Hello friends, today we are going to derive the important equation what we known as the Schrodinger's time dependent wave equation. So last time we have seen what is meant by wave function and its physical significance, and today we are going to derive the expression for the Schrodinger's time dependent wave equation. For that, consider the de Broglie's wave. So we are knowing, according to de Broglie's hypothesis, when a particle of mass m moves with velocity v, then the wave system is associated with it. Here, this particle can be considered as a wave. Here, this particle can be considered as a wave like this here, and this wave is known as the de Broglie's wave or the matter wave. When the particle of mass m moves with velocity v, then the wave is associated with it, and this wave is known as the de Broglie's wave or the matter waves. We are knowing this. So this wave is known as what here? The matter wave or the de Broglie's wave. Here, this is the matter wave. Matter wave. Here. The quantity which characterizes this wave is known as the wave function. So this is, suppose, and it is denoted by the symbol we are doing, that is psi. So psi is nothing but what here? The wave function which characterizes this de Broglie's wave. So consider the de Broglie's wave or the matter wave associated with the moving particle. The quantity which characterizes this de Broglie's wave or the matter wave is known as the wave function, or it is the variable quantity which undergoes the periodic changes and which is responsible for this de Broglie's wave is also known as what here? The wave function. This wave function is not observable quantity, it is not measurable quantity, it may be real or it may be complex. It will vanish when particle stops. Here the wave disappears and the value of psi is equal to 0. So the psi can be, it may be real or the complex, and that's why we will take the value of psi. The value of psi can be specified along the x direction. Here, along the x direction. Here, if suppose particle is moving along the x direction, then along the x direction, here the wave can be specified. Psi can be specified along the x direction by this equation. So it is equal to amplitude, that is a into e to the power. Instead of sine and cosine functions, for convenience we will use here the exponential function minus 2 pi I. Here minus 2 pi, here the imaginary factor, that is I, into bracket mu t, here the mu t minus, here mu t minus x by lambda. Here the wave is traveling along x direction, this is x, divided by, that is the lambda. So this is, suppose, the equation number 1. So what is the equation number 1 gives? The wave function for a free particle here in terms of the parameters of the wavelength associated with it. Suppose here the A is nothing but amplitude of the wave. Here the parameters of the wave are A is nothing but amplitude of the wave. Here A, mu is nothing but frequency of the wave. Here mu is nothing but frequency of the wave. Here, and lambda is nothing but the wavelength of wave. Here the wavelength of wave. Here. So these are the parameters of the wave here. So in terms of, this is the wave function of a free particle in terms of the parameters of the wave can be represented as a into e to the power minus 2 pi I mu t minus x by lambda. This is equation 1. Mu is frequency of de Broglie's wave, lambda is wavelength of de Broglie's wave, a is amplitude of the de Broglie's wave, and so on. Now what we have to do is that here we have to convert this, because this wave is not observable, measurable, and that's why we will convert this equation in terms of the physical parameters of the particle. The physical parameters of the particle are the mass of the particle, the energy of the particle, that is nothing but E, momentum of the particle, that is nothing but what here, T, and so on. So these are the parameters of the particle here. So these are the parameters of the particle, and these are interrelated here. these are interrelated. These parameters, physical parameters of the particle itself and the parameters of the wave associated with it here, that is A, mu, lambda, these are interrelated. And we will write this wave function in terms of the parameters of the particle. So for that, what we have to do is that we will use, according to Planck's quantum theory, according to Planck's theory here, we are doing, according to Planck's theory, Planck's quantum theory, Planck's law, we can say, according to Planck's quantum theory, we are knowing the energy of the particle. Energy of the particle when exhibiting the wave nature, it is given by h mu. It is equal to what here? The h mu here. H is Planck's constant. And this can be written as, so multiplying and divide by twice pi here. So 2 pi here, h mu divided by the 2 pi. So dividing and multiplying by twice pi, we are getting this equation. So this will be equal to 2 pi as it is here, 2 pi as it is, and h upon 2 pi becomes the h cut, reduced to Planck's constant, and here the mu, where the h cut is equal to h upon twice pi, and it is called as reduced to Planck's constant here. So h is equal to h cross is equal to h upon 2 pi. So from this equation, this is E is equal to, so we are getting this is E is equal to, so rearrange in terms of mu, so mu is equal to here, so rearrange this, we are getting E divided by 2 pi h cut here, the denominator 2 pi h cut here. If suppose this is the equation number 2, so what is the equation number 2? So according to Planck's quantum theory, we are getting like this, and we can write this equation. Also, according to de Broglie's relation, the wavelength of this, according to de Broglie's relation, we are knowing de Broglie's relation, what we call as d, according to de Broglie's relation, the wavelength of wave relation, the wavelength of wave is given by equation lambda is equal to, this is the wavelength of wave is equal to ratio of Planck constant, that is h, divided by momentum of the particle, that is p, where the p is nothing but momentum, and it is equal to product of mass and velocity of the particle. So product of mass and velocity gives rise to momentum of the particle, we are knowing. So this is known as de Broglie relation. The wavelength of wave associated with the moving particle is given by this equation. Now here, also here, we have to divide and multiply it by twice pi, we are getting here 2 pi h divided by here the 2 pi and p as it is. Again we will write h upon 2 pi is equal to what here? H cut. So 2 pi, we are getting here 2 pi h cut divided by what here? P. Here the h cut is nothing but again h upon 2 pi, it is reduced to Planck's constant. So instead of h upon 2 pi, you can write h cut. So suppose this is the equation number 3. This is the equation number 3. Now with the help of equation 2 and 3, so put the value of mu and lambda here. So this is the wavelength, that is lambda, in this equation number 1. So equation number 1 becomes here the psi is equal to, and remember that psi is function of position as well as time here. The psi is nothing but what here? The function of position as well as time. So psi is equal to, psi for simplicity we can not write here the bracket, but it is the function of position at the time. So psi is equal to A as it is, we are getting A as it is into e to the power minus 2 pi I as it is, minus 2 pi I as it is, in bracket here, in bracket we are getting mu t, instead of mu we will take e divided by here e divided by 2 pi h cut, here 2 pi h cut, here 2 pi h cut, and t as it is, here you are getting, so t minus here x divided by lambda. x as it is here, the x as it is, and the value of lambda is equal to 2 pi h cut. Here is nothing but 2 pi h cut, 2 pi h cut divided by p, means p goes to upper side numerator. Here that is the p. So we are getting this equation. So by putting the values of mu and lambda from equations 2 and 3, this equation 1 becomes, we are getting like this equation. Now observe, you have to 2 pi is here, 2 pi h cut is common, so taken out of bracket, and then 2 pi get cancels, and what remains is here it is equal to a e to the power minus I divided by h cut into bracket et minus px. Here the et minus px. So we are getting this equation. So the psi is equal to, like this we are getting equation. So this equation is known as the equation of the free particle in terms of the, this is the equation suppose 4 here. So equation 4 represents, this is the wave function of a free particle in terms of the energy and momentum of the particle itself. While the equation 1 gives what here? The wave function of a free particle, in terms of the parameters of the wave associated with it here, mu and lambda. So we will convert this equation 1 and 4 are equivalent. So it is in terms of the wave characteristics, it is in terms of the particle characteristics. The meaning is same. So that can be related with the help of the Planck's quantum theory and the Broglie's relation. We will take like this. Now we will differentiate this equation now with respect to t. So what we are getting here, delta psi by delta t. So delta psi divided by delta t. So this will be equal to differentiation of e to the power x remains as it is, and differentiation of power term. So a into e to the power minus I by h cut as it is into bracket et minus px, and what we have to do is that now into here the differentiation of the t coefficient of t. So minus I divided by h cut. So differentiation what we are getting, minus I divided by the h cut. So we are getting like this equation. So this equation becomes, so this will be equal to again. So we will take this term to this side here, the minus I e divided by h cut here minus sign, minus I e divided by h cut as it is, and remaining term a into e to the power minus I h cut et minus px becomes what here? It is become from equation 4, it is psi. So we can write this as a psi. So this is from, we can write e psi minus I e psi divided by h cut. You got the idea. So minus I e as it is, and whatever the remaining term, this much up to this much, is nothing but wave function psi. So we can write like this. Now rearranging this equation, E psi is equal to, so what we are getting here, E psi is equal to, so this will be equal to again delta psi, we are getting here delta psi divided by delta t. So this will be equal to, minus, this will be equal to, we will take this h cross to this side. So what we are getting, minus h cross divided by I here. So we are getting, or in other words, for simplicity we will write like this here. We will take this term to this side. So minus h cross divided by the I is equal to, minus is equal to into delta psi divided by delta t. So this will be equal to E psi. So we will convert in terms of E psi. So E psi. So this will be equal to here this term minus I by h cut we will taken to this side. So minus h cross by I delta psi by delta t as it is into E psi we are getting. So which implies here again, which implies this minus sign become I square we will take. So this is I square h cross divided by the I into delta psi divided by delta t. So this will be equal to what here? The E psi. So we are getting this E psi, and this will be equal to here. The I don't get cancels because I square become minus 1. You might be doing I square is equal to minus 1. So instead of minus 1 here, we will take I square. So we are getting this side, this equation. So I1 get cancels and remains I h cut delta psi divided by delta t is equal to what here? The E psi. So we are getting this equation. So this is equation say 5. So this is equation say that is the 5. So differentiating equation 4 with respect to t, we are getting this equation, that is equation number 5 we are getting. So this is the equation number 5. Again, differentiating this equation with respect to t, we are getting this. I h cut delta by like this. Now differentiating equation again psi with respect to now x twice time here. So what we are getting again here, what we are getting is delta psi divided by delta x divided by delta x. This will be equal to. So what we are getting here? So delta psi divided by delta x is equal to, as it is remains. So e to the power minus I by h cut as it is, minus I by h cut as it is, et minus px again here, the et minus px, a minus px into here the differentiation of what here? Into differentiation of coefficient of x. In the differentiation of x means we are getting coefficient, that is minus I by h cut, minus p become plus. So here the I we are getting ip divided by the h cut. So ip divided by h cut we are getting. Again differentiate this equation, what we are getting here? So delta square psi, differentiating again this equation we are getting second order differentiation, delta square divided by delta x square, and this will be equal to, again as it is we are getting a into e to the power minus I by h cut as it is here, et minus px here, and into differentiation of this again with respect to x. So we are getting this term double. So I square, here we are getting I square p square divided by h cross square. So this equation will be equal to here, I square become minus 1. So minus p square divided by h cross square here, minus p square divided by h cross square into, and whatever this term is nothing but psi. So we are getting p square psi is equal to minus p square psi is equal to like this, and from this equation we can write here h cross square here minus h cross square comes to this side here. So delta square psi divided by delta x square as it is. So this will be equal to p square psi. So this is equal to what here? The p square psi here. This term comes minus h cross square, we will take it to this side. So we are getting this equation, and suppose this is the equation number 6. This is the equation number 6 here. So this is also the main equation we are going to learn about. So that is the equation number 6. So by differentiating psi with respect to t, we are getting this equation 5, and again differentiating psi with respect to x twice time, we are getting this equation. Now recall here, the total energy of the particles. We are knowing total energy of the particle is sum of the total energy of the particle is sum of the kinetic energy, that is PEC, plus the potential energy, that is PEC. So this will be equal to total energy of the particle, that is E, which implies here. So this will be equal to kinetic energy, that is P, plus potential energy is nothing but what here? as usual symbols, that is capital V here. Now this will be equal to kinetic energy is nothing but half mv square, half mv square. Kinetic energy of the particle of mass m moves with velocity v is given by half mv square plus potential energy we will take as it is, that is nothing but here the capital V. Now here multiplying and dividing by m to this equation we are getting multiplying, so that m square here we are getting m square v square divided by here the twice m plus the v here. So we are getting this equation, that is v. Now m square v square means momentum square, so it is v square divided by twice m plus the potential energy, that is nothing but v here. So we are getting E is equal to, so what we are getting, total energy is equal to like this. So from this equation we can write E psi is equal to E into wave function psi is equal to p square psi divided by twice m plus v psi. Here we are getting like this equation. So suppose this is the equation number 7. So what equation 7? E psi is equal to like this. Now with the help of equation E psi is equal to, here we are getting E psi is equal to this term and p square psi is equal to this term. So using equations 5 and 6 in equation 7 we are getting this Schrodinger's time dependent in the equation. So by putting that values here we are getting so what we are getting, so E psi is equal to I h cut delta psi divided by delta t here. So this will be equal to, so E psi, instead of E psi we will using equation 5 write that, and instead of the p square psi we will write this equation minus h cross square. So what we are getting is minus h cross square divided by twice m, minus h cross square divided by twice m d square psi, here d square psi divided by dx square plus v plus here the v psi. So we are getting like this equation. So by putting the value of p square psi there, so we are getting that equation. So this equation can be written as, which implies I h cut delta psi divided by delta t. So this will be equal to, we will take psi common to this side, so minus. So in quantum mechanics, remember, in order to draw the common factors, you have to observe here this common factor to the what here, the right of this is also right of this is also right of this. So we have to take the common to the right of the equation. In here this side left here, so we have to take to the left side. In quantum mechanics, remember, the common factor and that deals to the operator, then that common factor will be taken to the left side or the right side depending on the position of that variable. So minus h cross square divided by twice m here, d square plus d square divided by dx square here, plus v plus potential function bracket complete and psi is here. So this equation is the famous equation which is known as the Schrodinger's time dependent wave equation. This is the final equation. Schrodinger's time dependent wave equation is given by like this equation: I is equal to delta psi by delta t is equal to minus h cross square divided by twice m divided by x square plus phi psi is equal to 0 in one dimension. This is the case of one dimension. To write this equation in case of the 3 dimension, what we have to do is that instead of this we can write like this. So this above equation can take the form I h cut delta psi divided by delta t. This will be equal to here the minus h cross square divided by twice m, and instead of this we can write using 3 variables: delta square divided by delta x square plus delta square divided by delta y square delta y square plus delta square divided by delta z square bracket complete plus phi here as it is, this bracket complete and this side. So in case of 3 dimension we can write like this equation, so which implies here the I h cut delta psi divided by delta t here, so this will be equal to minus h cross square divided by twice m, and instead of this bracket we will take one operator what we call as del square inverted triangle square plus the v psi here. So this equation is known as the Schrodinger's time dependent wave equation in case of 3-dimensional case. In case of 3-dimensional case, where the quantity, where the value of del square is equal to d square divided by dx square, here dx square plus d square divided by dy square plus d square divided by dz square, and is called as the Laplacian operator. It is called as Laplacian operator. This is the Laplacian operator. So this is the 3-dimensional Schrodinger's time dependent wave equation. So from this it is seen that the Schrodinger's time dependent wave equation is the unique differential equation. It is unique differential equation. Why it is unique? Unique differential equation because it is unique because it contains the imaginary factor I. The imaginary factor I, therefore it is unique differential equation in particularly mathematical physics or the quantum mechanics because it includes the imaginary factor I. So in this way we derive the Schrodinger's time dependent wave equation in case of 1-dimensional as well as 3-dimensional cases. In the next lecture we will going to derive the Schrodinger's time independent wave equation. What is the independent equation? And these two equations are the important equation in the quantum mechanics. These equations are the fundamental equation in the quantum mechanics, as same sense that the Newton's second law of the motion is the fundamental equation in the classical mechanics. In every branch of physics there is a fundamental equation. For example, in case of classical mechanics, Newton's second law of motion is the fundamental equation. In case of quantum mechanics, Schrodinger equations are the fundamental equations. In case of hydrodynamics, where the motion of fluid is given, in that case the equation of continuity is the fundamental equation. In case of space science, the Kirchhoff's law can be regarded as father of the space science. So Kirchhoff's law is the fundamental equation in the space science. So in the every branch of physics there is a fundamental equations, and that equation can be used to solve the many problems with corresponding branches. Okay, thank you.